So now we're actually going to go ahead and start delving into Rolle's theorem, which is, as you will come to find, very similar to the extreme value theorem. It's just a little bit more involved. And it's actually very crucial for when we're going to start delving into optimization. And so Rolle's theorem essentially tells us that if we have a function f which is continuous on the closed interval ab and is differentiable in the open interval ab, such that f of a is equal to f of b, which just tells us that the function evaluated at the two endpoints is equal to each other, then there exists at least one, and that's the key term over there, at least one c is a member of ab, of the open interval ab, such that f prime of c is equal to 0. And so the points at which f of x, or f prime of x is equal to 0, rather, these points over here, at which f prime of c is equal to 0, these are referred to as the critical values. The critical values, or you could also say the critical points if you would like. So the values would just be the c values themselves. The points would be, c comma f of c, right? So essentially, what Rolle's theorem tells us that if we're continuous and differentiable over a certain interval, and the kind of function evaluated at the two endpoints of the interval are equal to each other, then we're going to have a point at which the slope of the tangent line is equal to 0, or there is going to be at least one point at which our tangent line is horizontal, at which we have a horizontal tangent line, and these points are referred to as critical points or critical values. So let's do a couple of examples to actually illustrate this. So here we have f of x is equal to x squared plus 7x plus 10, and we're asked to find the critical points for x as a member of -6 to -1. And so first of all, let's actually see if Rolle's theorem holds, so we can guarantee that there are going to be critical points in this interval. And so we know that this function is going to be continuous, and it's going to be differentiable, right, because this function is just a parabola, and so it's going to be continuous and differentiable for all real numbers, let alone for our interval -6 to -1. And now all that we really have to check for is kind of this endpoint condition. We have to see if f of a is equal to f of b. And so in this case, our a is going to be -6 and our b is -1. So we need to check if f of -6 is indeed equal to f of -1. And so f of -6 would be, 36 minus 42 plus 10, which is, 36 minus 32, which is going to be +4. And then f of -1 is going to be 1 minus 7 plus 10, which is indeed equal to +4. And so here we have that f of -6 is equal to f of -1. So the boundary points are equal to each other, or the function evaluated at the boundary points are equal to each other. And we know that this function is continuous and differentiable over our interval. And so we know that Rolle's theorem is going to hold. We are going to have at least one critical point within this interval. To actually find that critical point, let's just use the fact that a critical point is defined as a point at which f prime of x is equal to 0. Let's go ahead and first of all find f prime of x, which is going to be, 2x plus 7. And then in order to solve for these critical values, we just have to set this equal to 0 and solve for x, right? And so if we were to solve for x, we will end up with x equals -7 over 2. And so that would be our critical point right over there. And we can actually verify that this critical point is within our interval, right? Because -7 over 2, that's around -3.5, and that is, as a matter of fact, located within the interval -6 to -1. And so Rolle's theorem does in fact hold true, and this is how we would be able to apply it. Over here we have another function, g of x, which is equal to x cubed minus 2x squared plus 9. And we're asked just to find the critical points of f. And so here we don't really care about a particular interval, we kind of just care about the critical points in general. And so let's go ahead and actually do that. So let's first of all find g prime of x, which is going to be 3x squared minus 4x. And in order to find the critical values, we just have to set this g prime of x equal to 0. So again, we can just go ahead and factor out an x here to solve for our critical values. And if we do that, we should end up with x equals to 0 or +4 over 3. And so these would be our critical values, right? And if we want to find the critical points, we can just go ahead and input 0 into our function and input +4 over 3 into our function. And we will end up with the critical points, but I'll leave that to you because I don't really feel like doing that. Now, the next part of this question asks us, does Rolle's theorem guarantee the existence of critical points for x as a member of 0, 2, for x as a member of the open interval 0 to 2? And in order to actually see whether this holds, let's first of all check whether the conditions of Rolle's theorem hold true for this interval. And so we know that g is indeed continuous and differentiable. For our interval, again, it's just a polynomial function, so it's continuous and differentiable for all real numbers. And what we need to do now is just check whether the function evaluated at these endpoints are equal to each other. So let's see, g of 0, right, which is going to be equal to just positive 9. As a matter of fact, 0 is one of our critical values. And then we have g of 2, so the other endpoint, which is going to be, 8 minus 8 plus 9, which is indeed equal to 9. And so here we have that g of 0 is indeed equal to g of 2. And so we can state that Rolle's theorem guarantees, or Rolle's theorem does hold true. Theorem holds for x is a member of 0, 2, right? And as a matter of fact, I mean, just looking at these critical values, even if we didn't find the critical values, we could still say that we are going to have at least one within this interval. But looking at it, 4 over 3 is, as a matter of fact, a member of our open interval from 0 to 2. And so that would actually be the critical point contained within this interval. And so that's how you can actually use Rolle's theorem and the notion of critical points in order to kind of understand how we can analyze different functions. And so as time progresses, we're going to start delving into optimization, and critical points will prove even more critical, to say the least.